Okay, so in this lecture, we are going to discuss the mathematical models related to the 3D geometry that are going to be used in the 3D neural networks that we are going to see in the second part of the course. So today we're going to discuss geometric modeling and mesh representations that are going to be used in these 3D networks. And we are starting with modeling of geometric models. So here we are going to distinguish between man-made geometry and geometry that is generated by nature. Okay? There are very different types of shapes, and then they require different mathematical models. So we start with the classical modeling that is used for computer-aided design and computer-aided manufacturing, so CAD/CAM systems. And we are going to see first the conceptual framework that underlines the classical geometric modeling, and then see what are types of models and descriptions for this manufactured objects, and see representation schemes that are really important to be implemented in CAD and CAM systems and make a reliable foundation for design and manufacture of these man-made objects. So going back to this conceptual framework, in the case of geometric model for man-made objects, in the physical universe, you have shapes that represent artificial objects, constructed objects by some artificial process. And then we want models that are going to describe the geometry and topology of these artificial objects. And these models are going to be represented by graphs or arrays with the data that are going to encode the geometry and topology. And finally, these graphs and arrays, they are going to be implemented using data structures, and they will be associated with standards for interchange of formats between different systems. So we are going to see, in turn, first analyze these shapes, artificial shapes, and then see what kind of mathematical models we can use to describe the geometry and topology of these artificial shapes, and then how to represent the geometry and topology discretely using graphs and arrays, and how to encode these graphs and arrays using standard data structures. So we are going to proceed in this order. Okay, so talking about shapes, we are interested in man-made objects. So these are objects that are generated by some process that's usually a craftsmanship built by hand, or industrial a process that in a manufacturing plant. And the characteristic of this shape is that they are piecewise smooth geometry, like planar surfaces, smooth surfaces, but they have some discontinuities, like an edge of a table and things like that, right? And also, usually these man-made objects are constituted by parts, so they have different assemblies. Like a chair has the seat, the back, the feet, and the same for a table or some other part. So this has to be taken into account when you model these shapes and you construct these shapes. So some examples of the man-made objects are like regular objects, like 3D objects created by some design process, or like constructed objects that are like buildings and other large shapes that are in our day-to-day environment. So basically, these are the all the shapes that we deal with in an urban area and at home, and these are not, as opposed to what you're going to see afterwards, shapes that come from nature. And then, what be the good mathematical model for this piecewise smooth surfaces and shapes? The option of choice here is manifold models. So manifold models essentially describes homogeneous point sets. So these homogeneous point sets has a property that they are locally Euclidean. So if you take a point into the shape, we can see, this vicinity of this point projected into the tangent space of the shape, and the tangent space is locally Euclidean. And this means that we can do all the operations that are used in mathematics, in calculus, integration, looking at the tangent space of these shapes and considering the geometry and topology in that fashion. So this gives rise to differential geometry, differential topology, and other things that we are going to use in the systems. And to describe these shapes of manifold models that are homogeneous point sets, we are going to use a deterministic functional specification. And basically, there are two kinds of functional specifications for manifold models that we are going to use. First is a parametric description, and then the implicit description. So they are both describes the shape of this set of points by a function, but they do in a different way. So the parametric description does it by enumeration of points, and the implicit description does it by classifying points of the space. And in that sense, they are complementary descriptions. So here we see that we have a curve, and this curve is parameterized by a parameter t. So as we vary the parameter t along this interval, the function gives us the points into D that belongs to that curve. So basically, it enumerates points of the curve by varying the parameter. And then the implicit description, you have this function G of the ambient space that basically takes to a point in space, it classifies the points. And so the points of the curve are the points for which this G function takes the value C. So all these points along the curve has the value of G of xy equals C. And so these other parallel curves have different value, like C plus epsilon, C minus epsilon. And here we can see that they're complementary because they serve for different operations in a modeling systems. So if you want to draw the curve, it's nice to analyze this, we use the parametric function, and then we plot the points by varying the parameter t. It's very easy to draw a curve like this. But then if you want to compute some interference of this shape with other objects, by classifying points related to the object, we can see that there is an intersection or things like that. So they are both very important, and they can describe the same shapes in complementary ways. And we are going to use this in the systems. So an example of describing an object using parametric and implicit, so notice that's the same object. Here we are describing the unit circle, and a parametric description of the circle basically varies the angle by sine and cosine. And as we vary the angle, we enumerate the points along the circle, right? But then an implicit description is totally different. It's given by this expression, x squared plus y squared equals 1. And basically, this describes the set of points that has a distance 1 from the origin. And so this is the definition of the circle. So these two are two equivalent definitions, and they serve for different purposes, right? For in this case, if I take a point that the value of x squared by y squared is not 1 but 2, then it's going to be outside the circle, and it's less than 2 be inside the circle. So we can do this kind of testing, right? And then here, if we want to plot the circle, it's just varying the angle theta, and then it's going to give the 3D points along the circle, right? So now we need to represent these models in a constructive way, a way that we can implement in a modeling system. And basically, if we have a simple shape, we call the simple shape a primitive. And a simple shape can be described using this deterministic functional specification, either parametric or implicit or both. But if we have a shape that is more complicated, then we are going to resort to take the primitives, our building blocks, and then use either a constructive approach or a decomposition approach. So if we take a constructive approach, we are going to combine these simple shapes using some methods to incrementally create complex objects from these building blocks. And the opposite would be taking a very complicated shape that we already know how it is, but we don't know how to describe it, and then break it apart into simple primitives. So these are two ways to describe and represent complex shapes by a model that is based on primitives, one assembling the primitives and the other decomposing the object, right? And here we are going to see examples of those, right? So an example of primitive representation is a system that has a shape library. And so the shape library can represent different primitives, like here, a cone, a cube, and a sphere. And then we have several supporting functions to manipulate these shapes and the primitives. And also transformations, because when you put this in a complete scene, we want to transform these shapes to put them together and things like that, right? And going back to the same example of a circle, here the primitive would have both a parametric and an implicit description. And in the system, the representation will be given by parameters that would be like the radius and identity of the object. Like here, you see that we changed a little bit. Instead of just representing the unit circle, we put the radius of the circle here. The radius is a parameter. And so the data structure that we are going to use to describe this primitive in the modeling system is by an associative array. So that associates the parameter with their value. So the radius with the value of the radius of the circle. And then we distinguish different circles by their identity and stuff like that, right? So this would be like a primitive representation. But then for shapes more complicated, we can have either a constructive or a decompositional representation. In the case of a constructive representation, we are going to have half space elements. Basically, you have the ambient space, and we have the set of points that belong to the shape and the set of points that are the complement, that don't belong to the shape. And then we are going to operations to combine this set of points, either point set operations or blending operations. So an example would be like there's a simple CSG model. And so the primitive here will be quadrics. So quadrics would include spheres, cylinders, and things like that, right? And then the operations would be point set operations like union, intersection, and difference. And the representation would be an expression in this CSG algebra that would have as operators union, intersection, difference, and operands the primitives. And so here we have an example of an expression that I have this complicated shape is the difference of the union of cube with sphere, this intersection of the cube with a sphere. Then you have this sphere with these parts cut out. And then we subtract the union of 3 tubes. And then we have this hollow shape here with these edges. And you see there is a correspondence between the CST expression and the data structure. That's a binary tree because these operators are binary operators, right? And so the representation inside the system is this expression that is implemented to this graph that's a binary tree, right? And then you have all the parameters associated with the parameters for this each primitive. And if we had like a blending operation, it would be similar, but with a different type of combination and other parameters to do different types of blending and things like that, right? And now the decomposition representation is the other way, right? Because basically what happens is that we have topological elements, and then we take a complete object and we break this object into simple parts that will be primitives, but we are going to assemble these primitives in terms of this topological elements. So basically here, the object is a shell, right? This, polygonal sphere, right? And then we break into faces, and then the faces we break into edges, and then the edges we represent the geometry by the vertices of each end point of the edge. And so in that sense, we have a topological graph that we have layers that corresponds to topological elements in a hierarchy. You know, the topology 0, 1, 2, 3 are dimensions, topological dimensions 0, 1, 2, 3. And then we construct this using this stratification. And this is very powerful because we can create this structure that can be manipulated, and we can define both the geometry and the topology by this cutting and gluing together these pieces, right? And so an example of this is a polyhedron. So basically, this is the model is a cell decomposition. The cells here are of dimension 2 that are faces, dimension 1 edges, and dimension, oops. And dimensions wow. Sorry about that. Okay, and the dimension starts like a cell decomposition that has the decomposition in cells with dimension 2 faces, dimension 1 edges, and dimension 0 vertices that are connected to create a mesh. And then there's a representation of the boundary of the shape of the shell. In the data structure, this is a list of polygons. The polygons are the faces. And in that case, it would be like a piecewise linear geometry because of planar faces, right? Okay, so now we are going to see these geometric primitives in detail. And then we first are going to study the functional primitives and then the mesh primitives, because the mesh primitives are very important in terms of implementation because they are using most graphic systems. So the functional primitives, you are going to see the concepts related to them, how to implement a system with functional primitives using a generic interface, and give an example of a primitive in this system. So the concepts here are that first, we are going to use a dual functional description. Because as I said, this parametric and implicit description are complementary. And so if a modeling system adopts like this dual functional description, this will be beneficial because it can use operations with either one of the kind of the description, either parametric or implicit, when appropriate. And then because it's a primitive system, we have a collection of primitive shapes that are in the context of the family of objects that we want to model and manipulate, and if it's a CAD system to design and build, right? So then we have here like typical objects like a sphere, cone, cylinder, quadrant, and etc. And the representation, as I said, they'll be given by the parameters of associated with the primitives, transformations, and also auxiliary structures like a 3D extent, like a bounding box of the primitive. So here we can see that we can build a generic interface using object-oriented implementation. Basically, we have classes, and generic classes will be like a primitive, and a primitive has its parameters, like a private data that belong to different types of primitives. And then the interface will be like through support functions that are going to be used to manipulate this in the system. And the advantage of this is that the system, when you implement the system, doesn't need to know which primitive it is, because it's going to talk the primitive through these functions. And so here we have functions that are related to the object itself, like create a new object, destroy a new object, and then functions that are related to the parametric description, like and then to implicit description, and to attributes, to transformation, to input-output. And so, for instance, for the here is this exchange. I'm sorry, it should be implicit and parametric. So the implicit, we want to classify the points, take the gradient of the points to intersect a ray with the primitive, and the parametric, we want to generate a new point to get the normal of that point to transform the primitive in some way. And then we have like functions that are related to attributes, like a texture in the object. So we have texture coordinates and manipulation of the textures. And then we have transformations by a 3D matrix and a transformation. And then operations to draw an object, to write an object. And this is very powerful because the object knows how to draw itself and take advantage of special characteristics of the object, right? And here, again, is an example of a sphere, or like in 2D, a circle. Then you have like a local coordinate system for this object, for the sphere, and it's represented by the center of in the radius. And we have to implement all these functions: a function to create the object, to destroy the object, to compute the bounding box of the object, to classify a point, to transform the object, and to draw an object, and other things like that. So this actual implementations of these virtual functions over here, right? And then when you go to mesh primitives, we have a different way to represent, because then the primitive itself are going to be associated with this piecewise decomposition. And we are considering here mesh primitive because we can imagine that when you use some piecewise decomposition, the elements there are primitives that you put together in a compositional way, as I mentioned here. Like here, a mesh is a way to implement this decompositional representation, right? And then the elements here, when you create a mesh, is a special type of primitive. And that's what is used in the most graphic systems that know to process polygons. Basically, we send a polygon to the graphics pipeline, and a graphics a card draws that polygon. And so, basically, important to study the mesh primitives and see the properties and how they are used in modeling and graphic systems. And there are different types of meshes. There are generic meshes, rectangular meshes, simplicial meshes, and there are different data structure for meshes. So we can represent meshes as a polygon list, polygon point graph, edge-based. And in the final part of this lecture, we are going to study in very detail the mesh primitives. But I put this here just to, see how a mesh is a special kind of element that surpass these representations in a modeling system. And we see that also the mesh not only describes the geometry and topology, but also gives other informations, like visual attributes, like surface colors, texture coordinates. And this is also used for both visual appearance and also to describe other properties, some material properties and things like that. So the structure of the meshes allows us to do this in a very standard fashion. And we are going to see this in the end of the lecture, final part of the lecture today. And then when we discuss the rendering systems and visual appearance, this is going to also be considered. And just to kind of put all this together in a concrete example, I'll take it as a case study, the Blender application that's very used for graphics and also in machine learning, and see how the shape modeling is done in Blender. And here we see the elements that we can use in Blender, and basically we have what we have seen for these geometric representations. I start with meshes, that's more common, and then you have surfaces, and then you have metaballs, and then we have curves. So meshes would be like the special mesh primitives. The surfaces would be like the compositional objects that are more general and would be like the composition representation. Metaballs would be an example of a composite representation. And then curves would be like auxiliary elements to construct and do modeling in Blender. So here we see the mesh primitives. We see that actually they have primitives that could have an implicit and parametric description, and also a mesh associated. And so here we have like a plane, a cube, a circle, a cylinder, cone, torus, and these elements that we say, oh, like I want this primitive, and then it gives the primitive and its association, and approximate description of the primitive through a mesh primitive, right? And then these surface primitives are actually the general decompositional representation of higher level the compositions, where here we have curved cells. It's not a piecewise linear decomposition, but in some cases we can precisely give the geometry through these nerves that no uniform rational B-splines. And this is very much used in the industry, in CAD/CAM systems, because when you want to build something, we want the actual geometry. And so this is used in the car industry, aerospace industry, and others. And then you have like metaballs that are a constructive example of model representation. Here we have implicit free primitives that are density functions. And then you have like these blending operations that you combine these different types of implicit primitives using this operations of a union, intersection, and a complement of these primitives, but in a kind of smooth way. So this would be like a blending of these different shapes. And this also gives a very powerful construct thing, and as opposed to CSG. CSG is more used for systems that are associated with the industry, CAD/CAM systems, and metaballs are associated with artistic systems, where you want more flexibility to describe these smooth shapes. And so this also is all implemented in Blender. And we also have curves that are used as auxiliary generative elements. So we want to build different objects. We create like a curve, and then you can use that curve as the generative element, for instance, surface of rotation or other types of shapes using the different modeling techniques. And so with all these elements, we have a very powerful modeling capability in Blender, and using those representations and some modeling techniques that we are not going to discuss this in the course, but essentially as a way to, in the system, to construct the shapes, and in the end have a representation that either a mesh or a compositional surface or a constructed surface. Okay, and now I'm going to make a pause here to go to the second part of this mathematical models for geometric modeling. And we are going to consider now to model natural phenomena. And you see that to model natural phenomena, we are using a procedural approach instead of having just a functional approach for describing the shapes. We use geometry and topology. We are using a sort of algorithmic approach to describe models that are created by nature. And in that sense, going back to our framework, we want to study the form of a natural object that comes as a phenomenon that's related to some physical process created by nature. And then we see that the mathematical model for this will be like through a virtual machine that implements different algorithms that are going to basically describe the properties of this natural phenomenon. And these algorithms are going to be represented through programs written in some programming language. And the implementation of this will be in a computing system that are going to basically run the processes to create the shapes the same way as nature creates shapes using physical laws and evolution laws. Here we are going to do the same thing in a mathematical sense, using virtual machines and algorithms that are described to programs written in language, and then in this system that's going to support all those dynamic processes. So in that sense, it's very different. And just as a remark, this is something that would be the next challenge for AI graphics and machine learning, because this gives a sort of a different, framework, and will be the next frontier of machine learning to really model this in the best way using artificial intelligence. And in that sense, we are talking about objects and phenomena that comes from nature. And the processes that are implied in this are like physical processes and growth processes. And so in that sense, the characteristics of this phenomenon, the geometry is irregular, the shape is usually amorphous, and typically they are dynamic, they evolve. And so examples of this type of models are living beings, animals, plants, and our environment. That is the product of the evolution and the action of environmental forces, right? And it's very important to model these kind of things because at this moment we are concerned with, a relation of the man with the environment and sustainability and understanding how this works. So we have this into using machine learning and artificial intelligence is very important for application. So this will be like the next frontier. And we are not going to discuss the implementation of this in neural networks very much into this course, but I want to give you a perspective what will be the next thing. And then what will be the mathematical model to support this kind of processes. There will be machines, but this have to take the understanding of these machines in a totally different way, because here I'm talking about machines over reals. These are not real computers. Machines over reals are a theoretical model of how you can envision these properties of natural processes in a fundamental mathematical way. And so this is the work of Steve Smale and Leonore Bloom. Steve Smale is a mathematician that has a Fields Medal and works in this area in dynamical systems and geometry and computation. And the idea here is that you have a very general point set and can be determined by deterministic or probabilistic process or a combination of both. And the abstraction is that you have a machine that in theory is very simple. Basically, it has like an input node, output node, a computational node, and a branch node. And this, just that is enough to describe any natural phenomenon. And the way we describe is like this. You have an input and output, and based on this input, you generate an output that's a point set. And the computational node is this transformation that manipulates point sets. And this, for describing a point set, this is the main result of this theory, is what we call a decidable point set. A decidable point set is shape, some form that can be computed by a decision machine over the reals. And so the proposition says that a set is decidable over R if and only if it's both a halting set of a machine of the real. So the set and its complement. And so if you can construct a machine that computes this set, we can describe any kind of natural phenomenon. So this is very general, and there are a lot of details how to come from the theory to the practice and implementation. Basically, to go from this abstraction to the actual implementation, we are going to use procedural representations. And so, and we can have different types of procedural representations. One that's functional based, there will be a representation, will be an expression, very much in the same way we saw like a constructed solid geometry expression. And by the way, I mean, like this description using machines over the reals is so general that encompasses all that we saw before for man-made objects. But it's more powerful because it can go beyond the simple things that just take into account geometry and topology for the classical geometric modeling. And so here we have the basic thing is like a functional based a procedural representation that implements a shape algebra with in the representation of the expression. And then we have a grammar-based procedural representation where we have parallel grammars. And here, this grammar basically describes the rule of a generative process. And you see that it's parallel, and this is in computational now, we can run this parallel in you know, like GPUs and things like that. And then you have like a procedural representation that's associated with physics process, physically based process, like constrained languages that are going to include simulation and structural relations. So I'm going to give examples of this next, right? So the functional based models, we have models that describes material and appearance. We have models that describes complex details, and also models that describes evolutive structures, right? And then so we have like procedural textures that maps from the support space to the attributes. And so in that sense, we can take into account the material properties of a shape and the appearance of a shape in a very complex ways. And for here, we use the tools of Fourier synthesis, smooth scale noises, and etc. And then like hypertextures goes a step further because applies modulation functions to a density function. So imagine like an implicit description, we have a density that describes smooth shapes. But if you want a shape that's very complicated or porous shapes, then you want to apply modulations that are going to describe that in a kind of a probabilistic way, to some kind of a stochastic process. And finally, we can have rules of evolution to evolve a shape, and then we start with some generator and generates the shape, evolving and growing the shape. And so we are going to see the implementation of these functional based models now. So start with noise-based. Actually, this is the work of a professor here at NYU, of Ken Perlin. In 1985, his PhD thesis from NYU proposed this model, and he proposed this model that gives like controlled randomness and is able to describe natural phenomena from the appearance point of view. And so this noise function is smooth, correlated, and band limited. And this is how you know, the Perlin noise looks like. And associated with this, it has composition operators like sign, multiplication, division, absolute value. And when you combine this noise function with the composition operator, in the right way, we generate the appearance of natural phenomena. And you see how that's done. So this, we see the composition. We have like this, the background with like just the noise in the 2D plane, the background. And then you have a sphere, the noise applied to the sphere. And so this first quadrant here is just the noise, the same appearance that I showed before. But then if you use a combination of a sum of noise using 1 over f, you basically change the frequency of noise at different scales. And then we have this fractal appearance, the fractal noise. And we take the absolute value of the noise in this sum of fractal noise. We have like a turbulent appearance here. And if we modulate this by a sine function, then we have this modulated turbulent fractal noise that looks like a marble pattern, right? And so using this as the language and ways to model this, we can create things like mountains, a material that's marble. And in the end of the course, we are going to see neural networks that take this model and generate, learns how to construct these expressions by learning from examples and things like that, right? Okay, so this is the noise. And then I would like to show, I'm not going to discuss the hypertexture, but the hypertexture is a kind of a extension of this, where we use noise and other things combined with implicit description that acts on densities. And here we are not considering, the geometry. We consider most the appearance. And then when we use the hypertexture, we incorporate the geometry in the same framework. So these two words, like procedural texture and hypertextures, are both a contribution of Ken Perlin. He started with his PhD thesis, and then he did subsequent work on that. So now I'd like to talk about the genetic procedural model. And basically, this is very powerful because it's a simulated evolution of biology. And we know that in nature we have plants and animals and other organisms that suffer a growth process and evolve. And the concepts here are the genotype and the phenotype. So the genotype is like the DNA, the structure of that organism. And the phenotype is the expression of the DNA that will be like correspond to that individual. And the genetic process incorporates these three elements. The generation of the genotype, that will be the expression of what we want to generate. And then the simulation is going to have these two components, a deterministic component and random components. So we have a selection that will be the fitness of the phenotypes, and we are going to select between different phenotypes. And then you have reproduction with mutation to create new genotypes. And then this will be like a random thing. And have like some probability distribution that's going to kind of determine how this goes, right? So concretely, the evolution process is like this. First, we start with an expression that has a genotype and a phenotype. And then we're going to reproduce this genotype with some number of other genotypes, phenotypes pairs, and there will be mutations when you do this reproduction. And then after you did the reproduction, we are going to select some using some random process, and then based on this rule, we are going to iterate, and this does take into account the evolution. So the algorithm is like this: the genetic algorithm is you generate a random population, and then you have this loop of evolution that to create a new population, we choose the parents according to fitness using the selection, and then we do a reproduction with mutation, combining parents to form childs, and you replace the current population by the new population. And then you keep doing this, and you have like an evolution that combines the deterministic and probabilistic aspects that are incorporated into the genotype and the phenotype and the rules of fitness and of mutation. And this is very powerful. Here is the work of Carl Sims to generate different types of plants and basically evolving plants and take into account very complex geometry, and actually he computed this into supercomputers like a connection machine and at that time in 1991. Okay, now we are going to talk about grammar-based models, and like some grammar-based models are also used to create the structure of this evolution processes, but using different kind of procedural method, right? So we have like basically geometric grammars and topological grammars, and the topological grammars are suitable to describe plants and these evolving mechanisms. And geometric grammars are shape grammars that are associated with fractals. And they are used to describe this very complex geometry that has self-similarity and associated with like some process like the action of erosion and things like that. And so starting with this grammar-based process, we have a parallel rewriting system that's based on a grammar and the application of the rules of this grammar in parallel recursively. And so here we have an alphabet of symbols. In this example, the alphabet symbol A and B. We have axioms that to be the initiator, that to be more or less like the pair genotype phenotype that starts the whole evolution. And then you have production rules that are substitution rules that belongs to the grammar. And this is more or less the same as those mutation and selection rules in the other example that I gave. And then the evolution here is the parallel application of the rules of the grammar in a recursive way also. So you see like here we start with axiom, the initiator A, and then you apply in parallel these rules, just two simple rules. A goes to AB and B goes to A. And then you apply this recursively, and then you have like a very complicated expression here, right? And then to actually use this, what you have to do is you have to interpret this code in a geometric way, because this is the structure of the growth, right? And here to model a tree, our grammar is like a tree goes to a branch or to a leaf. And a branch is either a cylinder or the tree itself. And then when you start and generate this, once you have that, you sort of like have to interpret and then substitute the branch by a cylinder, the leaf to the shape of the leaf. And what you get is this Renan is the representation of the real plants, and this was studied by Lindemeyer around the 1968, and it's Lindemeyer is a biologist, a mathematician, and this can model real plants, right? And so this is a very principal way. Both the genetic and this L systems are mathematical models that are inspired in biology and genetics. But they are built using these machines that are procedural and can be interpreted using the mathematical model of machines over the reals. And then you have fractals. And fractals, and they capture the statistical self-similarity of natural shapes. And this was studied by mathematicians all over the years and turned more popular with the work of Benoit Mandelbrot, that analyzed this in great detail. And here we see again this 1/f decomposition, because we have like this different scales that corresponds to different frequency ranges, and you see that in like parts like that in different scales, they look almost exactly the same, and in that sense they are statistically self-similar, and that's a characteristic of several natural processes, right? One way to create a terrain using this idea, and was devised in computer graphics during the era of computer graphics to create realism and simulate terrain, is this that uses a mesh and with a simple procedure to do random midpoint displacement. So here, again, we start with an initiator, a simple shape, in this case a triangle, and then the generator replaces parts of the mesh with subparts. Basically here, divides this triangle into 4 triangles and perturb the position of the vertices according to this 1/f pattern. And then applying this recursive procedure, you can result very realistic terrain models. And you see that in this case of natural phenomena, you have like different languages and different procedural systems that generate similar things. We saw like the noise function to generate the rain, and here like the fractal grammar generate the rain, and also saw for the genetic procedure and grammar based generate plants. So these are examples of things that natural phenomena that we have this systems, languages, and procedures to create and model these shapes. And finally, come to like a physics-based models. So these physics-based models, the name self-explanatory. They implement the physical laws of our world, and these are simulated in a computer system. And then we can distinguish like 3 main kinds of physics-based models. This one is also, there are many others, but like some very popular ones are the particle systems, that we have like a start values and motion equations in a simulated mechanism. And then when you apply this, you generate dynamic things, very powerful, or can be either static things, because you can freeze the evolution at some point. And this is used in like a game engines, like a Unity and Unreal, to model natural phenomena like fog and waterfalls and things like that, right? And then this particle systems, they can be coupled or uncoupled. So if you want to model like a cloth, you create like a particle systems that is connected by springs, and then you can model the elasticity of the cloth and things like that, the material. Also, like the formal models, you can model in it because like cloth, you can abstract a simple sheet of material and with springs. But if you have more complex models, like non-rigid objects that are solid, like a blob, a gel, then you have to create like a volumetric structure and then simulate the forces and how the material reacts to that. And the material can be elastic, inelastic. So you take all this into account. Basically, essentially, you apply physical simulations combined with a geometric modeling and computational system. And the same for constraint systems. Constraint systems are associated with articulated or kinematic structures. Human beings, animals, they have a skeleton, and the skeleton is an articulated structure like a robot also. And then you have constraints, and then you have a simulation how this can behave using physics in a real world. So again, like systems like Unity and Unreal, they employ like this kind of simulations for motion capture and things like that. And in machine learning, to train like robots or learn how people walk, you create a neural network that incorporates these constraints and train using, for example, reinforcement learning, and then you learn this, and that's how the cutting edge of robotics and autonomous driving and things like that are being implemented today. Okay, so now I'm going to make a pause for Q&A. Okay, so now in the second part of the lecture, we are going to concentrate on meshes. So as I promised in the first part, we are going to treat meshes in a special way because they are very important, both in terms of systems applications, and actually we are using in the course PyTorch 3D, that the main representation is meshes, and there are other representations, but concentrates on meshes, and meshes it's important as a representation in itself. And what I'm going to do is I'm going to discuss meshes both from the theoretical part and then implementation part. And we are going to go from the basic concepts of what is a mesh, what's a good mesh, to what data structures are used to describe a mesh and to implement a mesh in a system. Okay, so I'm going to talk about mesh representations, the main mesh classes, and data structures for meshes. So the mesh representation, the concepts that are behind the mesh representations are connectivity, regularity, and tilings. Because a mesh, if you think, like a point set is defined by points. A mesh has vertices that describe the geometry. But what makes a mesh is how you connect those points. And studying this, we can understand what is a good mesh. So the first thing is the concept of local connectivity. So local connectivity is how one point is connected to other points. So in a mesh, this point is a vertex, and then we have the notion of the degree of a vertex. The degree of a vertex is the number of edges that are incident to that vertex. And consequently, is the number of connections that that vertex has with other vertices, right? So here we have an example of vertex of degree 3, here the vertex of degree 4, and here a vertex of degree 5. And then using this concept of the degree of a vertex, the local connectivity, we can talk about topological regularity and define regular meshes. In a regular meshes, all vertices have the same degree. And this implies that all faces of this mesh have the same number of edges. And if you take surfaces that are going to be tiled by meshes, we have two types of surfaces: surfaces without boundaries and surfaces with boundaries. And the surfaces without boundaries, they are either closed or they are infinite. Like the real plane, the Euclidean plane stands infinite. And if you bend the real plane, you have surfaces that can go to infinite, and there's no concept of boundary, but it's not closed, it's open, right? But in practice, we also have, surfaces that has a boundary. The surface has a boundary. In that case, we have to distinguish the points that are internal to the surface and the points that are along the boundary. And in that case, I mean, we don't use this rule. Here in this is a regular mesh, and all this versus has balance 5. But here, this points doesn't have the same valence, right? And we are going to discuss this concept of surfaces with boundary and without boundary further on as we discuss meshes. And the concept of regularity here is topological. We can extend this to geometric regularity. And this is very important because it's related to planar tilings and it's related to crystallography. That means that it not only requires the topological regularity, but we require that elements, they are the same. And so in a tiling, we have a prototile that if we glue prototiles together, we create planar tiling. And in the case of the plane, they spans the whole Euclidean plane. And this is something that is used in crystallography and also to design good meshes. But the regular planar tilings, they are very restricted because there are just a few planar tilings with that property. Then you have like semi-regular tilings that the prototile doesn't have to have the strict regularity, but not strict regularity. So you have like here, for instance, these prototiles that they have different valences, and so they are not, because see here all the elements are the same, either squares or triangles or hexagons, but here you have elements that different shapes, but they are the same elements, and they have different valences for the vertices. And here this is indicated in this code. Like here we have a tile that has a 4 valence and 8 valence, and so this is a 4-8 tiling, and the same for these other ones, right? And this also is a semi-regular, because if you look at them, you see that they have similar regularity properties, but not strict like that. And this is also very important, and important also for subdivision surfaces and other things that we are going to discuss further. And then we need to consider how to classify a mesh. And we can classify a mesh according to the elements, the faces, to the structure of these elements, the topology of the mesh, as I mentioned before, and the combinatorics. Going to each of these criteria for the classification, we start with the faces, the mesh types. And considering the faces, this is related to the this regular tilings and semi-regular tilings. You have like a homogeneous meshes and heterogeneous meshes. So this, in this case, the mesh is composed of this same type of face. In this case, like a triangular mesh, all the elements, all the faces are triangles. And here's a general mesh. We have like triangles, hexagonals, quadrilaterals, and other things. So these are two streams of how we can build a mesh. And needless to say that the homogeneous meshes are preferred in most cases, right? And so, as I was saying, I mean, the homogeneous meshes are preferred, and the main types of homogeneous meshes are quadrilateral meshes, triangle meshes, and we have this that will be equivalent to the semi-regular tilings. It will be like a 3-quad mesh. Is a mesh that combines quadrilaterals and triangles, and so this is very useful. And so these are mainly used in most systems to that need good quality meshes. And then going back to mesh and topology, as I was saying, I mean, like we can have surfaces that are compact and not compact, and we have surfaces closed that are without boundary, and open, and then with boundary. And here I'm going to discuss the topology of closed compact surfaces. And there's this theorem that's very important in topology. That's the theorem of classification of closed surfaces. And it's very powerful because it says that, any kind of surface that's closed and orientable is either a sphere that has genus 0 or any tori that has genus greater than 1. And so this concerning the topology, any closed surfaces like that. And this is a property that is important because as you put together a mesh, you want the mesh to kind of respect if it's a closed surface. You can analyze and classify like this the topology. And then there are a lot of mathematics that you can do with that. And also there's the combinatorics, because in the beginning of the lecture, say we want to deal with manifold shapes. And the manifolds is locally similar to the Euclidean space. And so in a mesh, the manifold property means that a vertex around the vertex, you can, in the surface, if you consider the faces, you have a disk for internal vertex, or an edge, you have also a disk for internal vertex. And if the vertex or the edge belong to the boundary, is a half disk. So this will be like the topology of the Euclidean plane, in the terms of the mesh, considering the combinatorics. But then you can have structures that are non-manifold, where like around edges and vertices, the structure around them is not a disk or like a half disk. And this doesn't have a non-manifold property. And in practice, in a modeling system, if you enforce the manifold condition, you can do a lot of things, including you are going to see in the end of the lecture, for the data structure has a lot of implications. And then now, with that, you can analyze the properties of a mesh according to different characteristics. And these characteristics will be like the number of elements, the size of a mesh, the uniformity of the elements, how similar they are, the regularity, the distribution of valences of the mesh along this, the support, the shape of the elements will be like the aspect ratio of faces, and the directionality, if there's some directionality on the structure or not, there's isotropic or anisotropic. And if you take all these properties into account, you can say what is a good mesh. And here we have like a basic assumption that you have a mesh that approximates a surface. So the mesh is a discrete representation of a continuous surface. And in that sense, in most cases, unless it's a polyhedron, we are never going to be representing exactly that surface. It's a curved surface. There will be like some approximation of this continuous surface. And we want to take into account this approximation, but considering a criteria that are going to analyze these properties. And what happens is that using this criteria, we can consider the geometric tolerance, the structural smoothness, the isotropy or anisotropy that deals with those properties. Like the geometric tolerance, I'm going to discuss the error metric between the continuous surface and the mesh, but also it's going to take into account the mesh size. The isotropy and anisotropy are going to consider the quality of the elements, the quality of the faces, if the aspect ratio is good or not. That's important for like numerical simulations, like finite elements and things like that. And the adaptation, whether the mesh is adapted to features of the shape, the edges are aligned with curvature, lines of curvature, and things like that. And then the structure smoothness. I'm going to describe the variation, how the mesh varies these characteristics over the surface. The regularity and uniformity. And in a nutshell, I mean, like this, considering all these criteria at the same time, is going to give an approximation problem that has conflicting criteria, because it's impossible to get all these criteria satisfied because we have computing an approximation that depends on the shape that we are going to approximate. And also, I mean, the way to choose what will be the criteria that are more important depends on the application. So it's natural to pose this approximation problem as a constraint optimization. For instance, I would like to get the best mesh that approximates in terms of geometry, but with a certain number of faces, not more than that, or get the best orientation of features with bounded aspects, or the best smoothness with bounded variation. And so this depends, if you are going to use like a finite element simulation, it's very important to have bounded aspects. And so we have to consider this. If you are implementing a mesh in a game that has to run in a low computational power cell phone, you need a mesh that's low poly with the least number of polys that represent the shape in a way that runs in real time. So all these criteria depend on the application, right? But there's a principal way to pose this constraint optimization and compute the best thing. And with a neural networks, you can incorporate this in the neural network. And so just to finish, would like to talk about the main mesh classes that kind of have properties that can be used to build, this constraint problem in a nice way. And these are homogeneous mesh types. As I mentioned, they are triangle meshes. They have quadrilateral meshes, and this special one that's a triangulated quadrangulation. And so the triangle meshes, they are very important because in mathematics they are a simplicial complex. And this name simplicial is like the simplest combinatorial structure that you can do with mathematics and implement all the operations. And so the characteristic of this is that a triangle mesh typically is isotropic. And what we'd like is to simulate the planar tiling by triangles, and the dual will be like by hexagon, because you have like 6 directions and no preferable directions emanating from a vertex, right? And also, I mean, like it's irregular in the sense that the vertex are distributed in a irregular general position and don't follow any specific pattern. And in that sense, they are adapted because they can conform to the shape. And the operators that you use for triangle meshes are what they call bistellar moves, that belongs to topological combinatorics. And this basically, with these moves, you can convert any triangle meshes with from one type to another. And for the geometry, we use the parameterization with barycentric coordinates. And the main algorithms that we use for triangle meshes are algorithms for computational geometry, and the central algorithm is the Delaunay triangulation that guarantees a lot of properties for the meshes, right? Now, quadrilateral meshes are more or less the opposite of this, because the characteristic is that the quadrilateral mesh is anisotropic because you have a quad, you have 2 main directions, and here you can have like either regular or semi-regular meshes, and the parameterization will be like a rectangular parameterization, and here we have algorithms to take a surface and do quad meshing, and this means that like most of the vertices have valence 4, but some will have valence different than 4. And these are going to be called non-adaptive T-joints. If we want to kind of create subdivisions here, besides this extraordinary vertex that have valence different than 4, you cannot subdivide the mesh, otherwise you would get like a T-joint. So the mesh is not adapted. But if you want the adaptation, then you can resort to this triangulated coangulation that combines the best of quadrilateral meshes with triangulations. And this 4-8 mesh, if you remember, is a semi-regular tiling of the plane, because the vertices here have valence 4 or 8. And any mesh can be represented by a 4-8 mesh, a semi-regular 8 mesh, a 4-8 mesh with like some extraordinary vertex. And the good thing is that this triangle mesh has an underlying quadrilateral structure. So you see that here, the quadrilaterals are subdivided into triangles. So we have like this block, what you call like a basic block. And the basic block is a quadrilateral that's split in the middle into 2 triangles. And the characteristics, as I said, it's a semi-regular, and also is adaptive because we can subdivide. And here we have like also these stellar operators. And the powerful thing about this is that it can be adapted and have multi-resolution, because you can subdivide this basic block recursively. And you see that when you subdivide here, you create another mesh with quadrilateral triangles, but smaller elements. And then if we do 2 iterations of this, you repeat this basic block in the same position. And here we have a kind of a duality that this is like rotated by 45 degree here, right? And this is work that was done jointly with Dennis Oren, that's also a professor here at NYU, like around 2000, 2001. And this is very powerfully used in modeling simulation systems and in theory of subdivision surfaces. And finally, just to finish the class, I'd like to show this excerpt of a tutorial that Professor Daniele Panoso gave a while ago. And for you guys that are also taking geometry processing, he probably are going to present material more or less like this, and most of you have already seen this in this class. But for completeness sake, I would like to just show this to finish the lecture. And basically, it's about data structure for triangle meshes, because you saw the properties of a mesh, and I would like to see how to implement this in a good data structure, what are the choice that we have for the data structure. At the beginning of the lecture, I said, well, like we have the option of having just a collection of faces, an index set of faces, and edge-based structures. Then we're going to see what are the trade-offs between these different data structures and how they apply. So the first thing is that we have a data structure. So what should be stored in the data structure? As I mentioned before, we should store mainly the geometry, the coordinates of the vertices. That's what we're going to define the shapes. But we want to define the connectivity, the topology. So to be like the adjacency relationships that are related to all the properties that I mentioned just now. And also, as I mentioned in the beginning, different types of attributes like color, normals, texture coordinates. And these attributes can be, usually they are associated with vertices, but they can be also associated with faces and edges. And so we want to store all that in a mesh in the most efficient way. And what should be supported to manipulate these attributes? Well, first we want to render the mesh, the most important thing for graphics. But then for modeling, we want to do different types of geometric queries. Like, for instance, what are the vertex of face number 2? So we go in here, say, well, like a vertex EHD. And then is vertex A adjacent to vertex H? So we go in here, say, vertex A is not adjacent because it's not in the one ring here, right? And things like that, right? And also we want to have operators that are going to modify the structure of the mesh, either like removing a vertex, a face, to split and collapse edges. And these are the stellar operators that I mentioned before, right? And to do these geometric queries, we have to basically to answer all these queries about neighborhood relationships. Neighborhood of vertex to a vertex to an edge, and so on. There's a very big combinatoric structure here. But we also want to answer these queries very efficiently, typically, ideally in order 1 in terms of time, right? And this has to be encoded into this topological graph, right? That the mesh is a kind of topological graph, right? And so with that, you can say, well, what is the criteria for analyzing a good data structure for a mesh? And then what's the criteria for design the mesh given some application, right? And so, we can, decide what is a good mesh, analyzing the time to construct the mesh, the time to answer a question, time to perform an operation, how much space it takes, whether it's redundant or not. And for the design, depending on the resources we have, we can say, well, like I'm going to just to deal with shapes that are simple and the number of vertices are going to be low. This one thing, but if the shapes are too complicated and have a lot of vertices, then it's a totally different thing. And that's going to imply, in the memory that's going to be used, required operations and things like that, right? And so with that in mind, I mean, like, we can, in this area, I mean, there are 4 types of main data structures. And I'll put this observation here because this is implemented in PyTorch 3D. And then it's a good exercise to understand how these structures related to what's implemented in PyTorch 3D. Right? So we already mentioned this main data structure that's triangle list, index face set, a half edge data structure, and a radial edge data structure. And then you see that the first data structure is very simple. It's a triangle list, but notice that basically we describe each face by collection of vertices. Like it's a triangle mesh. We give the coordinates of each vertex and of the first triangle, then the coordinates of each vertex of the second triangle. And notice that there's a lot of redundancy and there's no connectivity information here, right? But this representation is good for this is adopted by the STL format that's using CAD for 3D printing, things like that, right? And then you have the index face set that is used for graphics in this like a OBJ format and others. And here the idea is like to not to have any redundancy. So we have like a list of vertices, and then the triangles are described as indices into this list of triangles. But notice that here, there's no explicit neighborhood information. We don't know which face is close to which face or which vertex connects to which vertex. But it's very compact as opposed to triangle list. That's a lot of redundancy. As a good compromise, we have the half-edge data structure. And here, it's important to notice that the half-edge structure applies to surfaces that are orientable to manifolds and exploits the fact that in a two manifold, internal edge is connected only to two faces, always to two faces. And a boundary edge is connected to only one face. And then we can do a trick that we represent half an edge. And half an edge is oriented because this mesh is orientable. And if you take these loops to compute the orientation, the edge that the half part of the edge that belongs to this face has the orientation that way. And to make things work, the other half has to be oriented in the opposite way. And so, take into account this property that we described before. So we design a data structure that has a vertex, a half edge, and a face. And the vertex is described by its position. So this here we have like the coordinates of this point in this vertex, and a pointer to an outgoing half edge index. And so you know that this vertex belongs to that half edge. And the half edge is the most complex part and encapsulates all the topology because it has a pointer to the origin vertex, has a pointer to the incident face, and has 3 points for other half edges. One from the previous in the loop, the other to the next in the loop, and another to the a twin half edge. So here, this one that has this is like this. You have one edge that has this bold half edge and this light half edge. And here is the pointer to the next and previous half edges. And so here we have the complete loop of this face. And all the connectivity is defined by the half edge. And then the vertex just kind of as a way to kind of go to a vertex to a half edge. And the face the same. A pointer that goes to the face to a half edge. And with this, you can do everything very efficiently. And so the best compromise for orientable surfaces. And almost all relationships you can do in O1 time, and modifications you can also do all in one time. The only thing here, I actually don't agree completely with Daniele that is heavy. I mean, like, is as heavy as it's needed because it has to store these pointers, and if you need them, you have to put them there, right? But the second comment is important. That it's not as trivial as the index space set for rendering in a graphics card, because like if you just want to render and not to do any other kind of modeling, perhaps the index face structure is better. But if you want to do real modeling, this is what you need, right? And finally, just to close, we are saying that this the half edge assumes that you represent a manifold surface, but there are some cases you need to work with non-manifold structures, because you can have like volumetric things where you divide the spaces into like regions, and to do this in an efficient way, you need a non-manifold mesh. And Blender actually uses this radial edge data structure as the basis of everything. And here you see that you have this non-manifold neighborhood along the intersection of these two surfaces, right? And another comment is that it's also based on edges, because it's for surfaces, edge is a special topological element. But here, what's taking advantage is that we have the edge as a main data element for the structure, but we consider different uses of the topological element. So you have a face, then you have a face use, you have a loop and a loop use, you have an edge use, a vertex use, and all that goes to a shell, that goes to a region, that goes to a model. So this is a way to easy to represent regions that are encapsulated by shells, and here you see that those uses. You can imagine that the half edge is like consider two uses of an edge in an orientable manifold. Here, in a general case, you have to put the use for everything, but the central topological element is the edge. And that's it. Let me close.